Hello.
Hello, sir.
Do you have any doubt from last class to anyone of you? Yes, Asma. So let's start new part of this chapter, that is potential energy stored in a wire. Suppose there is a wire attached to any support having actual length L till this part. Now, if you apply any deforming force to stretch it further along this direction, let's say F, so it will get slightly stretched till this point. Total elongation from this point to this point is small l. But this elongation, that is small l, must be achieved in this particular wire in stepwise. Initially, it was at this point. At some time, extension will be till this point. At some later, it will be till this point. And finally, it will be at this point. We can say this. This particular extension produced in this wire may have achieved in stepwise. So in last part, from this point to this point, suppose deformation is dy, and rest of the term from starting to this point, let's say y. And I'm just considering y is comparable to L, as dy is very small or infinitely small segment. Is it clear? Maria?
Yes, sir. Yes, sir.
So consider a wire having length L, area A, is attached to vertical support So if you apply force to its end, so force according to Young's modulus, as we had y equals to stress divided by strain. So stress is force divided by area of cross section. Strain is y times capital L. So on rearranging, it will be F times L divided by A times Y. So you can write F equals to Y times A divided by L multiplied by small y, which is equivalent to F equals to K times of X, what we have done for string. So if you relate these two equations, you will say K equals to Y times A divided by L. So this particular term will be called as spring constant or force constant. Is it clear?
Yes, sir.
Sumaira, any doubt?
Yes, sir. No, sir.
Okay. Now, to stretch this particular wire slightly by dy, we must apply some amount of work done, which get converted into potential energy, as spring force is conservative in nature. So if you do any work against conservative force, amount of work done gets converted into potential energy. And that will be equivalent to potential energy stored in this particular wire. So first write it down to this part.
Yes, sir.
Done, sir.
Mohiuddin, you have written?
Yes, sir.
Asma?
Writing, sir. So could you scroll a bit up? I'll take a screenshot.
Just 1 minute. Okay.
Done, sir.
Okay. So now let dW amount of work is done to stretch wire by dy or small displacement dy, which will get stored as potential energy. So work done equals to force times displacement. Put the value of force from the above part, it will be YA divided by L into small y times dy equals to work done. In this expression, capital Y is constant, that is Young's modulus. A is area of cross section, which is also constant, and capital L is a constant term. So keep it outside. Here we have y times dy. So to get complete part, we have to integrate. So on integrating this and this, you'll get amount of potential energy stored. So on integrating this work done, you will get total potential energy equals to YA divided by L. Here we have y raised to the power 1. So according to the rule of integration, if x to the power n times dx integration, it will be equals to x to the power n plus 1 divided by n plus 1. So we have y raised to the power 1. So using this formula, it will be 1 plus 1 divided by 1 plus 1 and limit. Since extension in this wire is from this point, that is from y equals to 0 to this point, that is y equals to L. So limit will be from 0 to L, from 0 to L. Is it clear?
Yes, sir.
Asma, any doubt?
No, sir, no doubt.
Okay. Now we can write YA divided by L. Here 1 plus 1 will become 2 and y square. Limit from 0 to L. So put the value of y to be upper limit as small l and then y equals to 0 as lower limit and subtract them. So it will be YA divided by 2 times of L squared to be upper limit and 0 squared to be lower limit and subtraction in between. So on rearranging, you will get half YA divided by L into L squared equals to total potential energy stored. Now we have to convert this particular expression in terms of force and extension only. So you can write it as half YA divided by L into small l times small l. This particular term, since y is equal to L, so we can write force equals to YA divided by L small y, which will be equals to YA divided by L into a small l. So this whole term will be equals to force. So this expression will be half times force into extension in wire equals to potential energy. Miriam, is it clear?
Yes, sir.
Shiraz, any doubt?
No, sir.
Okay, just write it down.
Done, sir.
Done, sir.
You'll have written? Asma?
Over, sir.
Shiraz?
Done, sir.
Now we have to convert this particular expression in terms of stress and strain, since most of the question will be in terms of stress strain only. So how to relate this particular term as potential energy equals to half times force times extension. So if you divide this whole expression and multiply this whole expression by same term, this fraction will remain same. So divided by volume and multiplied by volume. So it will be half force into extension. Volume is area of cross section times length multiplied by volume. Now this whole term is nothing but force divided by area of cross section, which will be stress. And the second term, change in length to the original length, is called strain. So this will be half times stress into strain times volume equals to potential energy stored. Is it clear?
Yes, sir.
You can rearrange this particular equation in terms of Young's modulus also, as Young's modulus equals to stress divided by strain. So you can write stress equals to Y times strain, or strain equals to stress divided by Young's modulus. So if you put these two expressions in this part, you will get potential energy equals to half Y times strain square into volume, or half times stress square divided by Young's modulus times volume. So according to the given in terms question, you may use this different formula to find potential energy stored in wire. Is it clear? Muhiddin, any doubt?
No, sir.
Okay, just write it down.
Done, sir.
Done, sir.
You all have written?
Yes, sir, written.
Okay.
Written, sir.
A wire having dimension 4 mm square into 2 meter is hanged vertically a force of 2 into 10 to the power 5 Newton is applied. Find first stress, second potential energy stored if Young's modulus is 2 into 10 to the power 11 Newton per meter squared. Try to solve this using the above formula. Using this, you may write it in two parts. As length of wire is 2 meter and area of cross section is 4 mm square. Force is 2 into 10 to the power 5 Newton. And Young's modulus is 2 into 10 to the power 11 Newton per meter squared. As we have stress equals to force divided by area of cross section, just put the value of these two terms. Before that, convert this area in terms of their SI unit.
Hello, sir.
Yes.
Sir, sorry, I joined late. I had messaged over there.
Okay, no problem. Good, Muhiddin. Good, Mariam. To convert this area into meter square, just multiply it by 10 to the power minus 6. Now put all the values in this part. We have force 2 in 10 raised to the power 5, area of cross section 4 in 10 raised to the power minus 6. So it will be 2 divided by 4, 0.5 into 10 to the power. Here we have in denominator 10 to the power minus 6. On moving to numerator, it will become plus 6. And we have already 10 to the power plus 5 in numerator. So on combining, it will become 10 to the power 11. So this will be amount of stress applied on that wire. Now, according to the formula, potential energy equals to half times force times extension. Next is half times stress into strain into volume. Next is half times stress squared divided by Young's modulus into volume. So depending upon the given term in the question, you may use these different formula to find potential energy. Try to solve.
Sir, can you just show what you did in 30 minutes?
Okay, just 1 minute. We have started from this part, how to calculate potential energy stored in a wire. You may take screenshot from this.
Yes, sir. Taken. Sir, taken. Sir, taken.
And this is the last part we are doing.
Yes, sir.
Just use the first formula, put the value of force and extension produced if you have. Otherwise, use this third formula. Since we have calculated stress, we have Young's modulus, and you can solve volume, which is equals to area into length. this is capital L, actual length of the wire. But in the formula, we have a small l, which is extension produced. Okay, Sabita, just 1 minute. I'm using the third part, half. Stress we have calculated above as 0.5 into 10 to the power 11 square. So it will be 0.5 into 10 to the power 11 whole divided by Young's modulus, which is 2 into 10 to the power 11 into volume. Volume is area of cross section to length. Area of cross section is 4 into 10 to the power minus 6, and length of the wire is just 2 meters. Now, on simplifying it, this 2 and this 2 will cancel out. 10 to the power 11, 10 to the power 11 will cancel out. This 2 will cancel out this by 2. So on multiplying, you will get 0.5 into 10 to the power 11 minus 6. It will be 5 joule. Good, Mohiddin. Shiraz, is it clear?
Yes, sir.
Asma, any doubt related to this problem? You all have written?
Yes, sir.
Just 1 minute. Aisha, Sabita, you may take a screenshot. Sabita, done?
Yes, sir, done.
Okay. Next is, there will be some substance for which there will be only elastic limit. There is no plastic limit, no breaking or ultimate stress. So those substances are called elastomer, such as rubber band, thermocol, and so on. If you compress thermocol up to a particular small displacement, it will get compressed easily. But if you remove deforming force, it will come back to its original state in a while. But if you compress a little bit more, it will be broken. It means the substance which has only elastic limit, no plastic behavior, those substances are called elastomer. And if you draw graph, this is stress and this is strain. So graph or curve will be like this. Till this point, on removing deforming force, it will tend to return back to its original state, but from different path. So maximum amount of deformation or stress withheld by this object without breaking is called saturation point. So on extension, it will follow this path. On returning back, it will follow along this path. So there is change while going along extension and returning back with respect to stress and strain. So if you draw horizontal line and if you draw a vertical line, you will say while extension, stress and strain will be at this point. But on returning back, stress and strain will be at this point or be at this point. It means stress and strain, just 1 minute. It should be strain. So while going up and while coming down, stress and strain should not be proportional in extension or compression. They should lag with each other while going up or coming down. This property of object is termed as hysteresis. Since we are defining for any material, so this is called mechanical hysteresis. So first, what do you mean by elastomer? So you'll say the substance which has only elastic limit. There is no plastic behavior or plasticity is called elastomer. And these substances can be used to absorb shock during traveling or jerk. So these are substances used for shock absorbing. So greater the area of stress strain curve for that particular substance, there will be good shock absorber. So you'll say greater the area of stress strain curve, the substance will be good shock absorber. And last, since in extension and compression, they are not going along same way, or they should be not proportional to one another, there is lagging behind property of one with respect to another. While going up, stress is changing more rapidly as compared to strain, but going down, strain is changing more rapidly as compared to stress. So stress and strain are not directly proportional to each other while going up or coming down. This behavior is called hysteresis or mechanical hysteresis. The lagging behind property of stress, strain with respect to one another on extension or compression. Is it clear? Asma, any doubt? Samaira?
No, sir.
Savio?
Yes, sir.
Okay. Just write it down.
Done, sir.
Done, sir.
You all have written?
Yes, sir.
Asma? So on the basis of this, there will be a question. This is a stress and this is corresponding strain. So one will be so you'll be asked which of the two material is good shock absorber. So you'll say, since in the second part, area of cross section is more, so it will be good shock absorber. Is it clear?
Yes, sir.
Savio, is it clear?
So can you explain it once more? I didn't understand.
In above part, I just defined you in this statement. Greater the area of a stress strain curve, it will define you the substance will be good shock absorber. Since elastomers are generally used for shock absorbing, while transportation of any good from one point to another, let's say television, computer, AC, fridge. Similarly, on the base of this, I've just drawn two different graphs. If you see for the first part, area swept is very small, but for the second part, area swept is large. So which of the two substances will be good shock absorber according to the above condition?
So
So
B.
you'll say good. Yes, Asma, do you want to ask something? I'm unable to hear you. You all have written?
Yes, sir.
Just 1 minute, Asma. Just see in this particular graph, let's say for extension, this is for extension, and this is for compression. Let me define you another curve. Suppose there will be curve related to y and x as straight line. You must have learned this particular graph in class 10th for Ohm's law for voltage and current. So in this graph, y and x is directly proportional. So if you increase the value of y, there will be corresponding increase in x. So it will move linearly along this direction. And if you decrease the value of y, there will be corresponding decrease in x. So it will move along this direction as well. So you'll say for any point, let's say at this point, while going up or while coming down, x coordinate and y coordinate is same. Is it clear? But in this graph, for a stress strain curve, let's say for going up, at this point, strain is at this point and stress is at this point. But while coming down or compression, for the same stress, strain is at this point, or for same strain is at this point. So are they equal for extension or compression? So you will say no. While extension, stress is at this point and strain is at this point. But while compression, for same stress, strain is at this point, which is slightly different from this point to this point. Similarly, you can say for the same amount of strain, there is difference in stress. Initially, it was at this point, but now it is at this point. So you'll say stress and strain are not increasing and decreasing in same manner. There is some change. While extension, rate of change between stress strain is different, and while compression, a rate of change in stress strain is different. This difference behavior or lagging behavior of one with respect to another is called hysteresis. Is it clear now?
Yes, sir.
Okay.
Yes, sir.
Now there will be another question. Suppose you will be asked, if you hang a wire freely from any support like this for a long time, would there be any change in its length or not? Mariam, if you hang a wire which may have some mass freely for a long time, would there be any change in its length?
Sir, due to gravity, yes, over time.
Good. Suppose if you consider this particular strip, for this particular section, there is some amount of wire behind it, which must be applying some force to this segment by gravity to increase its length. This is called extension in a wire due to its own weight. Extension in wire due to its own weight. So you'll say at any instant, there will be some segment of wire behind it, which must be applying some force due to gravity to increase its length. So amount of extension produced equals to force times actual length divided by Young's modulus into area by 2. So this will be the total amount of elongation produced in a wire due to its own weight. Is it clear?
Yes, sir.
Asma, any doubt?
No, sir.
Okay. You all have written?
Yes, sir.
Yes, sir.
Arslan, any doubt? Shiraz?
Yes.
Let me define you one last term, that is Poisson's ratio. Suppose you have a wire so if you stretch it a little more, due to its extension, there will be change in its width as volume of object will be constant or same. So it may acquire this shape. So initial length of wire is this much. On applying deforming force, change in length is this much, due to which there is change in its diameter or radius from this point to this point. So there is two different types of deformation in this. First is along its length, which is called lateral strain. So lateral strain is elongation divided by its original length. Correspondingly, there is change in its width, which is called, just 1 minute. Longitudinal strain, which is along its length. So it will be delta L by L. Lateral strain is deformation in its width. So it will be delta D divided by D. As diameter of this wire is decreasing, so there will be negative sign, or you may write this particular fraction in terms of radius. So it will be delta R by R. Is it clear?
Yes, sir.
Yes, sir.
Now, if you take the ratio of these two deformation produced in this wire, this ratio is called Poisson's ratio, defined by sigma. So it is equals to lateral strain divided by longitudinal strain, which will be equals to minus of delta D by D divided by delta L by L, or minus of delta R by R divided by delta L by L. As in numerator and in denominator, both having same strain, which will be unitless quantity. So Poisson's ratio is unitless quantity. Asma, is it clear?
Yes, sir.
Now, for a rigid body, sigma equals to 0.5. So you'll be asked this to define the numerical value of Poisson's ratio for rigid body, which means there is no change in its volume. In practical, sigma lies from 0 to less than 0.4 or -1 less than 0.4. This is theoretical value of Poisson's ratio. And this is practical value of Poisson's ratio. Just write it down till this part.
Done,
Yes,
sir.
sir.
Yes, Asma.
Done, sir.
This lateral strain is also called transverse compression strain. You all have written? Aisha? Sigma is Poisson's ratio. Savio, you have done?
Sir, just a minute. Done, sir.
Asma, you have written?
Yes, sir.
So this is all about this chapter, that is mechanical properties of solid. Now let's start new chapter, that is mechanical properties of fluid. First, what do you mean by fluid? So you'll say the substance which having tendency to flow is called fluid. Matter having tendency to flow, just like liquid and gas. for this particular fluid, first define what do you mean by density. So density is crowdedness of particle. So it equals to mass of substance divided by volume. For water having maximum density at 4 degrees Celsius, density is 1000 kg per meter cube, or in terms of gram, it will be 1 gram per centimeter cube. Now, to define a ratio with respect to any other substance, we use a term that is relative density. Relative density equals to water having maximum density at 4 degrees Celsius. I will define this part in next chapter, how density of a particular substance or volume of a particular substance changes with temperature. Relative density equals to density of any substance divided by density of water at 4 degrees Celsius. So this would be a ratio which having same unit in numerator and denominator. So it will cancel out. So relative density will be unitless quantity. This is also called specific gravity. Is it clear till this part?
Yes, sir.
Sabita, any doubt?
No, sir.
So we mainly divide this fluid to study into two parts. First is hydrostatics. Means study of fluid at rest. And second is hydrodynamics. Study of fluid in motion. In hydrostatic, you will learn first pressure, Pascal's law, and various application. Second is surface tension and its various application, as Archimedes' principle is omitted from your syllabus. Second, for hydrodynamics, first is flow, viscosity, and its various application, and the most important, Bernoulli's principle and its various application. Just write it down to this part.
Done, sir.
Done, sir.
Done, sir.
Done, sir.
Done, sir.
Done, sir.
Okay. So let's start with the first part, that is pressure. Suppose you have a surface like this, on which force is applied. Let's say one is along this direction and the other is along this direction. Then there may be along this direction and so on. So there is a term which is called thrust. Mariam, do you have any idea what do you mean by thrust?
The perpendicular force acting on an object.
Good. So thrust is force which is perpendicular to that surface. So perpendicular force acting on surface is called thrust. So in this, we have F1, F2, F3. F2 is perpendicular to the surface, so it is called thrust. So pressure is defined for perpendicular force acting per unit area, or you'll say thrust acting on surface per unit area is called pressure. So pressure is the thrust acting on a surface per unit area is called pressure. So pressure equals to thrust divided by area of cross section. Thrust is a force having unit Newton, area meter square. So SI unit is Pascal or Newton per meter square. And since it is directional less quantity, so it will be scalar in origin or scalar quantity. I will define you this particular property of pressure. That's why it is called scalar in Pascal's law. Is it clear?
Yes, sir.
Asma?
Yes, sir.
Yes, sir.
Just write it down. I'm giving you a
Yes.
problem related to this.
Answer.
Done, sir.
A force of 0.2 Newton is applied to inject a pin on a surface if area of cross section is 0.5 mm squared, find pressure. Just use the above formula and try to simplify. Good Moeddin. Good Mariam. Good Samara. So have you just checked your calculation? We have force equals to 0.2 Newton. Area of cross section is 0.5 mm square. So multiply this whole term by 10 to the power minus 6, convert it into meters squared. Now use the above formula for pressure and simplify it. Pressure equals to force divided by area of cross section. Force is 0.2. Area is 0.5 into 10 to the power minus 6. So decimal and decimal will cancel out. So it will be 2 by 5, which will be 0.4, 10 to the power minus 6 in denominator. On moving to numerator, it will be plus 6. Now, if you shift this decimal towards the right, there will be degrees in power of 10. So it will be 4 into 10 to the power 5 also Pascal. Asma, is it clear?
Yes, sir.
Shiraz, any doubt?
Understood, sir.
Okay. You all have written?
Yes, sir.
Written, sir.
We merely have to define pressure for liquid. So first is pressure due to column of liquid, which is also called gauge pressure, denoted by PG. To derive this, suppose liquid is kept in a vessel up to this level. Now, in this container, just consider a small cross-sectional part, this cylindrical segment. Which has vertical column, height h, area of cross-section of base is A, and density of liquid is rho. So consider a cylindrical portion having height h, area of base A, and density rho. So for pressure, we just need two different terms. First is force, and second is area of cross-section. Force may be exerted by this column of liquid. So force exerted by this column equals to mass times gravity. We may convert this mass in terms of density as mass is equals to density into volume. So it will be density into volume into gravity. Volume of this cylinder will be equals to area of base into height. You must have learned about volume of cylinder as pi r square h. This part, pi r square is area of base and h is its vertical height. So you may use area of base into vertical height as volume of that geometrical figure. So volume equals to area into vertical height into gravity. Now for pressure, force exerted by area of cross section. Force is rho A H into G. Area of cross section is A. So this A and this A will cancel out. So you'll get P equals to rho G H. This pressure is due to column of liquid. So it is also called gauge pressure defined by PG. Is it clear? Or do you have any doubt in this derivation? Muhiddin?
Sir, what is AH here, sir? The volume of the cylinder, right?
Yeah.
Okay, sir.
You must have learned volume of cylinder as pi r square h. So this pi r square is nothing but area of the circular base, which may be written as A into h. So this will be general formula for calculation of volume of any geometrical figure. Asma, any doubt?
No, sir.
So what is that area of?
Area of base. You all have written?
Yes, sir.
Yes, sir.
Yes, sir.
Now, in this formula, we have three different terms. First is rho, gravity, and this height. Rho is density of liquid. G is gravity, that is acceleration due to gravity. And H is vertical column of liquid. So you'll say this gauge pressure mainly depends on just three factors. There is no any indication of direction in this part and amount of liquid above to that particular point. So you'll say pressure due to this column of liquid will be independent of direction and independent of amount of liquid. Means this is independent of direction and independent of amount of liquid. Let me define you what it means. Suppose you have a container in which liquid is at or up to this level. Now draw a horizontal level at a particular depth. Let's say H. So for this cross section, pressure along this direction is P1, along this direction is P2, along this direction is P3, and along this direction is P4. So according to the above condition, you will say gauge pressure or pressure due to a column of liquid is independent of direction, which means in all direction at same depth, it will be equal in magnitude. So P1 equals to P2, P3 equals to P4. Is it clear?
Yes, sir.
It means at same horizontal level in same liquid, it acts equally in all direction. At same horizontal level in same liquid, it acts equally in all direction. This statement is also called Pascal's law, which I will prove you later. And that's why pressure is called scalar quantity. Asma, is it clear?
Yes, sir. Clear.
Okay. Similarly, suppose first write it down to this part.
Done, sir.
Done, sir.
Savio, you have written?
Yes, sir. Written.
Shiraz,
Done, sir.
similarly, suppose there is different shape of container but connected together like this. And if you start filling liquid from any side, so level of liquid in each container will be same. It means at equilibrium, pressure difference between any 2 points will be 0. That's why there is no flow from one terminal to another. So if you calculate pressure at same depth in each, let's say this is P1 and this is P2, and P5. As depth of liquid from its top is H in same for all these 5 different shapes of container, but amount of liquid is different in different container. So as I defined you above, pressure at same depth will be independent of amount of liquid. So it will be P1 equals to P2, P3, P4, and P5. So pressure just depends upon strip of liquid placed over that particular point only. It will be independent of amount of liquid present as a whole in whole container. Is it clear? Samaira?
Yes, sir, clear.
Okay. Asma, any doubt?
No doubt, sir.
Okay. You all have written?
Yes, sir.
Yes, sir.
Savio?
Done, sir.
Okay.
No.
Done, sir.
Next is atmospheric pressure You must have learned about this in your earlier classes. Atmospheric pressure is pressure exerted by air or atmosphere on all objects living on the surface. So it will basically pressure due to air or atmosphere on object on surface. So we have to calculate its numerical value. For this, suppose mercury is taken in a container up to this level. This is mercury. Now suppose inverted tube or capillary tube is inserted like this, which is initially evacuated, which means there is no air inside it. Now, suppose this is point A and this is point B. I have taken mercury in a container and placed a capillary tube inverted and which is evacuated initially. So this is capillary tube, a tube which is very thin in diameter. Now, if I ask you to define pressure at point A and point B, are they equal in magnitude or they will be different? So Myra, is the pressure at point A and B are same or different?
Different.
Which one will be larger in magnitude for point A or point B?
A.
Okay, so you'll say pressure at point A is due to air above it, or that is atmospheric pressure. So at point P is pressure due to atmosphere. Let's say this is P0. And there is no any vertical column above at this point P as this tube is evacuated initially. So pressure at point P initially will be 0. Is it clear to all?
Yes, sir.
Now, since we have some pressure difference between A and B, so due to this pressure difference, there will be change in or transfer of matter from higher pressure to lower pressure. As point A is at higher pressure and point B is at lower pressure, so there will be flow of mercury from higher pressure to lower pressure. That's why level of mercury in tube will start rising till this point. Experimentally, it was calculated vertical column is 76 centimeter. Is it clear to you all? Why the level of liquid or mercury being raised up in this particular B or
Yes,
tube?
sir.
Asma, any doubt?
No, sir.
So at equilibrium, when there will be no flow from point A and point to point B, so you will say pressure at point A is due to atmospheric pressure. So pressure at point B will be due to its vertical column of mercury. So at equilibrium, pressure at point A equals to pressure at point B, and this will be equals to atmospheric pressure. According to the above concept of gauge pressure or due to column of liquid, it will be equals to rho GH. If you put the value of rho, that is mercury here, whose density is 13.6 into 10 to the power 3, gravity is 9.8, and vertical column raised is 76 centimeter, so divided by 100. On simplifying it, you will get 1.013 into 10 to the power 5 Pascal. This is called 1 atm or atmospheric pressure at ground level or sea level. Is it clear? Mariam,
Yes, sir.
Asma, is it clear?
Yes, sir.
You may have learned this particular term in your earlier classes as 76 centimeter of Hg. This is the representation of pressure or atmospheric pressure in terms of vertical column of mercury. 76 is vertical column or height, and Hg is of mercury. So if you put this part in above formula, you will get 1.013 10 to the power 5 Pascal. Just write it down to this part.
Done, sir.
Done, sir.
You all have written? Savio,
Done, sir.
Shiraz. Okay. So do you have any doubt till this part in fluid?
No, sir.
So let's stop here for today. In next class, I will define you how to solve different problems related to gauge pressure and this atmospheric pressure or combining them. Okay.
Yes, sir.
Okay, then we'll meet in next class.
Thank you, sir.
Thank you.
Thank you, sir.
Okay, thank you.